equivalent, and they yield exactly the same thing. And so the preference-based approach, or this normative approach, where we think about how people should make choices, is particularly appealing because it allows us to go to the utility function. And so what I've shown you is that we cannot, for all types of preferences, get a utility function. So for example, we're missing the lexicographic preferences. We also need to make certain other assumptions on preferences. But ultimately, there's a large class of preferences for which we can generate these utility functions. And we've also shown that these utility functions, so for every continuous preference relation, we find a continuous utility function. And this continuity is mathematically helpful because it makes it easier to work with. What makes it even more easy to work with is if your utility function is differential. That we did not talk about. So we need additional functional preferences to get actually a differential utility function. So there's kind of a step, an additional step needed where we somehow restrict the preferences to map to certain classes of utility functions. But there are certain utility functions, such as the Douglas, which I will talk about, that have very nice properties, that are very easy to work with, and because they're very easy to work with, we use them widely, even though they may not capture all kinds of preferences that individuals are having. So if we have this differentiable utility function, so this is what we started yesterday, then we can set up a utility maximization problem. So basically what we're doing there is we are maximizing the utility which depends on the bundle of goods that we are choosing, a bundle of commodities. So again, this is a vector. And what bundle here is also the Lagrange multiplier and the budget constraint. So we can only buy things for which we have money, essentially. And so I write here the minus, but actually so I have here a negative multiplier, but usually I write it as a positive expression, and I actually think that the positive expression is nicer. Because you can also write the Lagrange function plus lambda, and then you just have omega minus p times x. And if you approach it this way, sorry, I just started a little bit early, but feel free to come in just because I know a lot of people are going to the macroeconometrics and we are being recorded just now as well. So, right, so these are just different formulations. I actually even go on the slides, I have it now the other way around, it is irrelevant for mathematics, but I actually make an interpretation of what I just added to the slide more because it gives you a positive interpretation of the lambda. And what I really want to talk with you about for the next few minutes is what lambda means and why lambda is important and what is actually the intuition behind this Lagrange setting that we're doing. And you have done Lagrange throughout your bachelor's, I'm sure. Who has done Lagrange throughout your bachelor's? Everybody has, right? Yes. And so basically we get these first order conditions. And so this is what I wrote up here, because this was a little bit quick yesterday. So here I have this Lagrange reformulated. I'm putting this in a two-group world. So there are two commodities, x1 and x2, they both live in x. And so suppose we have this Cobb-Douglas utility function. So we have x1 to the power of alpha times x2 to the power of beta. And then what we can always do is we take the derivative with respect to x1 and x2, and then we can solve for this, and then we get the optimal amount of x1 and x2. Now, these optimal amounts, when we have Lagrange, always look the same. So, if we have the Lagrange function x1 times to the power of alpha times x2 to the power of beta, then we know that the optimal amount of x1 equals alpha divided by And so it is a feature of these Cobb-Douglas preferences or these Cobb-Douglas utility functions that you're spending a constant share of your wealth on a certain good. So the way you can see this is by putting the prices to the other side. So we always have that P1 x1 star equals alpha divided by alpha plus beta times omega. And so the share, again, the share of your wealth that you spend on a given good remains constant. So the P times X, that is always a constant for each of the goods. And that's it's just a specific feature that other utility functions do not have. And now assume, make a few more assumptions, maybe assume that alpha is equal to beta is equal to 1/2. Assume that all the prices are equal, and then what we get is that you spend half of your wealth on good 1 and half of your wealth on the good 2. Okay, so this is pretty standard stuff. What I want to talk about now is what does this mean for lambda? So how do we find, based on what I've done here, how do we find lambda? Are there questions? Feel free to ask questions if I was too fast. If you have a question. But how do we find the lambda? I mean, we have everything in numbers now, right? So we can calculate it from base.
We will let lambda alone by putting the other unknown values to other side.
Exactly. So basically, yes, you're correct. So we can just so we have all of these numbers, and so we take basically here the first expression. I'm just going to make this a star, and so what we have here is that this star expression that must be equal to 0. Why does it have to be equal to 0? What does it tell you if the first derivative is negative?
Negative means some loss, profit loss.
No, it just means, mathematically speaking, you're correct. But mathematically speaking, it just means, right, that we have a function that is decreasing. So just a random, let me just put here a random x, or let me put a random y, actually, just to flag that this is not the same as the x's that I'm talking about. And then we have a function f of y. And so this is now a decreasing function, and so we know that the first derivative of this decreasing function, and that must be negative because that's what it tells us, right? And so basically the first derivative is just the curvature that we're seeing here, and this is negative here throughout, and so we have this increase. So now, what x1, but the derivative of the function that we are looking at is negative. So that means that this function is what? Decreasing. It is decreasing, right? And so what this means is that as I'm increasing x1, that means if I buy more of good one, then I'm making a loss. So I dislike x1. And so I should reduce my x1 down to as much as I possibly can. But now I've already solved for this and I found my x1, and my x1 is just 1/2 of the wealth. And then my wealth level must be positive because otherwise I'm having not a well-defined problem. And so we know that this person likes sum of x1. And so therefore it must be the case that this is actually an optimum. And so therefore we can set this equal. So I'm just going to erase this. This was just a side comment. But if we're reformulating the structure here, is then we have that alpha x1, alpha minus 1, beta minus lambda p1, that must be equal to 0. So again, the question, what is our lambda?
Like just to derive it, I think we have to plug in x1 and x2 optimally and then solve for lambda.
Excellent. And what do you get when you do that?
If we assume we get lambda equals p1 divided by p2.
P1 divided by P2, that number would be equal to 1. Is this what everybody else gets? So, the array, I would love this. So I know that here I have alpha and beta are the same. So what this means is that, and I also know that x1 and x2 are the same. So what I have here, let me just call this x, I have here x to the power 1/2 and divided by x to the power 1/2, right? Because alpha minus 1 is minus 1/2. And then I have minus lambda, and that must be equal to 0. And I'm dropping here the p1 because the p1 is equal to 1, which is the example that I'm solving, right? So these two cancel out, this becomes 1, and so my lambda is exactly equal to my alpha. And so my alpha is equal to 1/2. And so my lambda is equal to 1/2. So what does this mean? If my lambda is equal to 1/2.
To get one more thing that we are wishing for, we need to let go of other stuff. One and two. Okay, one must to increase one for the other product. We should decrease 1.5 of the other product. To get more to reduce.
No, it actually doesn't have anything to do with how much of the one product versus the other product you're consuming. So the lambda comes in with a constraint, right? So if my lambda goes up, so to speak, the Lagrange part goes up. And this would increase your utility, and the answer to this is 1/2. So if wealth increases, unit utility would increase by 1/2. So this is what's happening here. And so now what does it mean that this is strictly positive? In light of this interpretation. So suppose this was 0. We had a shadow price of wealth and that was 0. What would that mean?
That our wealth wouldn't matter if we always would have the same utility?
Exactly. So our wealth would not matter. So additional wealth would be worthless to us. Exactly. And so, and therefore, this is what motivates, this type of interpretation motivates why we have this complementary slackness condition. And this complementary slackness condition is exactly this point 5. So this is what I'm after, what is the interpretation of what we have on the slide here. And so what we have on the slide here, if I just look at it for good 1, I have that the derivative of the utility at the optimal amount of the good minus, with respect to x1, minus lambda p1. This is just my first order condition, times x1 star is equal to 0. And so this first part here, this is just the marginal utility of good 1. Again, at the optimal amount, this is the marginal cost that I'm paying of good 1 times this lambda. And so what the lambda here gives you additionally in a sense is this good that you're paying for cost you something in terms of the price, but it also means that if you're buying x1, you're foregoing part of your wealth, and this is where the lambda kicks in, right? And so this is why we're multiplying this with the lambda. And overall, we multiply this with the x1 star. And so we either have that this first order condition. Use a different color here. So we have that this is the first order condition of the Lagrangian. Either this is equal to 0, or the x1 star is equal to 0. And so we're going back to what we started out with. So either we are in an optimum, or we would like to decrease the consumption of x1 because x1 does not add any utility, but we can only decrease our consumption of x1 down to 0, and so we're setting x1 equal to 0. And so one of these two parts must hold. Either x1 is equal to 0, or we have an optimum. An interior optimum. Let me say an interior optimum. Because x is equal to 0 can also be an optimum because it minimizes your losses. And so this condition is also called the complementary slackness. would not give me utility, and so therefore I have no value from it, and so therefore, if I can only buy this good that gives me no value, I have no additional, I don't want more wealth because I cannot use the wealth for anything that I get. That's kind of how this ties up, right? Does that make sense? Right. So this is how to interpret this lambda shadow price of income. We have the complementary flatness condition, and so one of these things must be zero. Right. Now, what we've worked towards is we found the optimal amount. And so now we can plug these optimal amounts back into the utility function. And what that gives us is the indirect utility function. So this is this term V of P times V of P and W. So it depends on the prices and wealth. Why does it only depend on prices and wealth now? So, right, what I'm doing here is I'm just plugging in these optimal bundles. Let's go back to the Hop-Douglas example, right? So there, the optimal bundles look like this, okay? So these are, so these are my optimal bundles. So now, if I plug them back into the utility function, what I'm getting here is, sorry, for the example of Douglas, I get an indirect utility function. So we have u of alpha over alpha plus beta, w divided by p1, and we have a beta over alpha plus beta, w divided by p2. Right? So because these are just the optimal goods, and so this is what I'm plugging in. And so ultimately what I'm getting is just a function v of pw, and so p is again this vector which contains p1 and p2, and I have these little alphas and betas so floating around, but these are just parameters of the utility function. But ultimately, the parts that we are economically interested in are prices and wealth, and so we now have a function, we have basically the overall value of the problem, and this is what the indirect utility is, which tells us how much utility is in the optimal achievable, depending on the prices we're facing, depending on the wealth that we're facing. And that's what is ultimately relevant, right? Because we're assuming that people make the best choices for themselves, and so this is what people will end up with. And so this is then crucial, for example, if we are interested in a price change on individuals' well-being, then what matters is obviously how this indirect utility function changes. And so in order to understand how this utility function, indirect utility function changes, it is worth understanding what types of properties it has. And so the first property is that it is homogeneous of degree 0. What does this mean? We had this at the beginning of this topic yesterday. To give you a hint. So homogeneity in degree 0 means that if I double prices and I double the wealth, then I still have exactly the same utility. Right? And so this is what we already had for the demand function. So let me move back here for of Douglas is a function of prices and wealth. Now we have also this output, so basically we're scaling up the price and we're scaling up the wealth by the same factor. And what we are buying is the exact same, because these relative changes, like if everything changes in the same manner, it does not matter. Only relative changes matter. And so, this is something that carries over to the indirect utility function. If my prices double and my wealth doubles, it is as if nothing has happened. So, this is what we have here. So, the indirect utility is strictly increasing in wealth. Why is that the case?
We are talking about a homogeneity of the Gefei-FIONA.
I just asked why is 0 not 1?
Oh, because it's, so if it was 1, then so the way that it works is you're multiplying because it cancels out, right? So what you can, let me go back to the example, that's a good question. So you are multiplying here for this utility function everything according to this factor. Let me call it A to not confuse it with the other alpha. AW divided by AP1. And so you can see that this also becomes AW AP2, and so the A's just cancel out. It is as if they are not there. Homogeneity of degree 1 would mean that if you multiply each of these variables by this A, you're multiplying the utility by A. So this is when we're talking about constant returns to scale. Do you remember the constant returns to scale back in the day when we were talking about production functions? So remember, you have a production function and then we just do a substitute case. So your production function, this is very much inside, but your production function is a function of labor and capital. Now, you scale up labor and capital both by the amount A, and so this is equivalent of A times L plus K, and so this production function would then have, would be of homogeneity 1. But that's just not how we finish. Right. So, strictly increasing in W and above. Why? Do you want to give it a shot? Because wealth is a good thing. That's very simple, right? So implicitly, what we are assuming here is that there's at least one good that we like. We could also frame this as we want to avoid some bad and we're willing to pay for it. But there is at least one good that we spend money on for whatever reason. And if there is at least one good that you spend money on for whatever reason, it means that you value this to some extent. And so this means that your utility must go up. And so the more wealth you have, the more you can spend on that good, and the more your utility goes up. And so therefore it must be the case that overall your utility is increasing as well, strictly so. And finally, we have that it is non-increasing in PL for any L. So let's talk first about why is it, under what circumstances is it decreasing in PL? So the higher the price of a good, the lower your indirect utility. Why is that? Because you have to spend more on your optimal amount, and so, or you might then reduce the consumption of that good L, but that also lowers your utility, and so adjustment process overall reduces the indirect maximum utility that you have. A more interesting question is, why is it non-increasing? Meaning, why can it be the case that as PL increases, nothing happens to the indirect utility function? So the utility function doesn't change. Under what circumstances is that possible? Think of the case where, in these settings, it's always useful to think of the case where your price becomes very extreme. So think of a price PL that goes to infinity, or some arbitrary super large number. What do you do if you have a commodity, if you see a commodity for which the price is just super high?
You stop buying it?
You stop buying it. And so basically, at some point, you reach this cutoff where you're like, okay, this good is just simply too expensive for me. I stop buying it, I only buy other goods that are cheaper. And so then an additional increase in my price has no consequences for you, because you're already not buying the good. And so, well, the price of the good becomes even more expensive. Think of a yacht. Like, rich people can afford yachts. I personally could not care less about the price of the yacht. It does not affect my utility function, because no matter what the price is, F does not pay me enough to buy a yacht. So that's the example. Okay, now, what can we do with this function? With this indirect utility function? So what is nice about it is that we can also start from this indirect utility function and back out what the optimal consumption level for each of the goods is. And so basically, what we have is that the optimal amount of good L is minus the derivative of the value function with respect to the L divided by the derivative of the value function with respect to W. And by value function, I mean indirect utility function, but it's also the value of the product. So why do I call it that way? And what is the envelope theorem? So let me just do a short excursion into the envelope theorem, because the envelope theorem is a mathematical tool that I think is very, very useful to have and to know. Okay. The envelope theorem states that at the optimum, and this is why it applies to the indirect utility function, because there we are at the optimum, only the direct effect of a parameter affects the utility. Okay, so to make sense of what I just wrote here, let me go back to our Lagrange problem. So for our Lagrange problem, we maximize the Lagrangian, and here I'm, for a change, going to be explicit what the Lagrangian actually depends on. Namely, it depends on the consumption bundle that you choose, but it also depends on the prices as well. And then this is equal to the utility plus lambda g of x p w. And so here I'm just denoting basically our budget constraint as a function g. maximized. And this D is really doing a lot of work, so and that's why I'm underlining it here. And the maximized Lagrange can then be written as L star. It depends only on P and W, right? Because we can now replace the x's through the P and W's because they're only functions of P and W in any case, and it's the utility function. It is the utility of x star here. I'm just leaving the x star plus the lambda star g of x star p w. So I'm left here the x star and the lambda star. But of course, the x star and the lambda star, both of them, are functions of p and w. Does everybody see why also our Lagrange multiplier is now a function of p and w? Yes, no. This is it's a binary choice. If you don't see it, you don't see it. Do you see it? Yes. Excellent. Cool. So now we have the L star, which is also a function here. So in principle, we can plug all of this in, which I'm going to do now. So we then have the Lagrange, which equals u of x star of pw plus L star pw g x star pw p and w. Right, so this is the entirety of our problem. And so now what you can see here is, right, that this L star is affected by P and W directly, in particular through the effect on G, and it is affected by indirectly because P and W affect the X star and they affect the L star, and then the L star and the X star affect the Lagrange values. But what the envelope theorem tells us is that this indirect effect, the effect through the L star and the X star, do not matter. What I want to do with you now is I'm going to show you why it does not matter. So if we are taking now, so this is really about comparative study, what happens if something changes. And by something I mean now, suppose the wealth changes. So then how much does the value of the problem change? So to look at this, we take the derivative of the maximized Lagrange value with respect to W, and we take into account the changes in the x's. So what we get is delta u, to save myself this entire dependence here just because it's tedious to write, delta x, delta w plus delta u, delta partial w, plus delta partial lambda partial w times g plus the second line here plus L star and the derivative of this g function, which was our budget constraint with respect to x, our derivative of x with respect to w plus, again, our Lagrange multiplier times the derivative of g with respect to w directly. Okay, so now we can look at the different bits and pieces. And so the first thing that is worth looking at is the part where we take the derivative with respect to the x's. So this and this. Okay. And so if we connect here these two terms, what we can write is delta u delta x plus lambda star delta g delta x, and this entire expression is multiplied by delta x delta delta. And so what do we know about this expression here? This should look familiar. It is familiar. You know this. Remember that this is the derivative of our budget constraint with respect to x. So this is just our price of that good that we're looking at. And so this is our standard first order condition that we get out of the Lagrange. So we have here, so this is our first order condition. This is our first order condition. And that is equal to 0. Because we're at the optimum. We've chosen optimal. And so, therefore, we can ignore this part, and we have already simplified our expression significantly. Now, we also know something about this g function. Again, this is our budget constraint. What has to hold an optimum? What always has to hold for the budget constraint, in fact, it's not just the optimum. Your budget constraint holds with equality, right? And so what this means is that your g function is equal to 0. This is just budget constraint. And so this part here, that is also equal to 0 simply because, and here I'm being in some sense too general, right? Because our utility function does not directly depend on the w. It just depends on the w through the indirect effect on the x. And so this is also equal to 0. And so the only thing that's actually left is this part here. So what we have here is our, so we can simplify the Lagrangian with respect to w, and that is just equal to L star delta g delta w. So now another question, what is the derivative of our budget constraint with respect to w? The budget constraint is w minus p1 x1 minus p2 x2. No, 0. That's your budget constraint formulated in this g way. So now if your w goes up, what happens with the derivative? 1. Do we all see that as 1? Yes, some people are not good enough. Okay, so yes, our derivative is equal to 1, and so here our derivative is simply equal to L star, and that's it. And now, this intuitively makes sense, right? Why does this intuitively make sense? Because lambda star is the shadow price of wealth, right? So if my wealth goes up marginally by 1 unit, then the value
x1?
Minus x1 plus
Minus x1, yes.
Yeah, no, you're correct. So, so exactly. So we have here minus lambda star x1 star, because again we're at the optimum, right? So that's why I'm also adding this thing here, and they don't look like stars, but they are meant to be stars. Actually, you can draw this much nicer. So now we have this, and so now what we can do is we can now divide these two things, and so what we have, if we divide as we have the derivative with respect to w, we have the derivative with respect to p1. Now I did it p1, and here we have the w, and that is equal to x minus, and that is equal to x1 star. And so now, this is close to what we have here, right? So we started this entire exercise to show that you can back out from this indirect utility function what the optimal amount of consumption of good L is, of the commodity L is. And we are close, but not quite, because the difference is, so what we have here are the lambda stars and not the V stars. But I'm going to say, I'm going to make an argument that the two are actually the same. Why are the two the same? Because the G and the optimum is equal to 0. And so the value of the problem of the Lagrange is actually equal to the value of the problem of the ux star, and the ux star is equal to the value function. And so, even though we have basically proven the envelope theorem in a different way, we established this, we can then invoke it and we can say, well, it's enough if we just deal with the indirect utility function. That's it. That makes it like this. Roy's identity. Interpretation. What does Roy's identity tell us? So, if your price, so we can rewrite this obviously. So, if your price PL is reduced by a little bit, then you get an additional income, which is the price change multiplied by how much you're actually spending on that commodity. Now, at the margin, the utilities of all the agents for each of the goods, they must be the same. And they must be equal to this expression here. So how much your indirect utility changes, right? And so obviously, your marginal utility also depends on the prices at this optimal, right? And so it's not, it's not independent of that. But ultimately, what this means is that the price reduction increases the consumer's utility by this amount, and that's exactly what we have here. And so here's a minus because we have talked about a price reduction, but obviously the left-hand side should be a price increase, and then you have this reduction on the other side, right? And so this is how it goes together. But in practice, it's just much simpler. That was utility maximization, just on a different, a little bit higher level. Questions about this? This is nothing that you've not seen before. You've done all of this utility maximization. The goal of this lecture is a little bit frame this, well, connect this a little bit to the fundamentals of the math, but why we see what we are seeing, and why intuitively these things make sense and how they tie in together in terms of the wealth. What does the wealth actually deliver to us? What does the complementary slackness mean? But also how we should respond to changes in wealth and prices. And these are obviously important because we are simply interested as economists how people respond if their wealth and if their prices change. Right? And so this is what allows us to do that. Now, I want to turn to the expenditure minimization problem. And so the approach is a little bit similar to what we've done with choice, right? So with choice we have two different approaches and we get the same result, and this is what we can do here as well. So you know the utility maximization problem, but the question is, well, what if you're not maximizing utility but minimizing your expenditures subject to reaching a certain utility level? Do you get the same result? And the answer will be yes. How many of you have done expenditure minimization, just out of curiosity? Nobody. Okay, let's do expenditure minimization. So I'm going to go a little bit slower here. So the expenditure minimization, what it does is it minimizes price times the amount of consumption of all the goods, such that the utility reaches some minimal utility level. And so let me just go in here and have a look at what this means again. Some more cocktails. And obviously we have two groups. So we minimize P1x1 plus P2x2. And we minimize the subject to x1 alpha, x2 beta is equal to u bar. And so this u bar is just some fixed utility. Why am I writing here the equality? So here we have a larger equal sign, here we have an equal sign. Why does it make sense? It makes sense because we want to spend as little as possible to where this utility bound is still fulfilled, right? And so if we're reaching a higher utility level, we can still save more, we can minimize our expenditures further and still reach an acceptable utility level, and so therefore that's what we want to do. And so for this reason, we also have an equality here. What are we minimizing with respect to? X1 and X2. So we have here X1 and X2. Now, we do the same thing as we always do because it does not matter whether we have a minimization problem or maximization problem, we set up our Lagrange. And so we have here P1x1 plus P2x2, because this is now our objective. And our constraint is u bar minus x1 power of alpha x2 power of beta. So then we take the derivative of this Lagrangian with respect to x1. And so what we get is P1 minus alpha lambda alpha x1 alpha minus 1 x2 to the power of beta. And I'm just ruling out here that there's a corner solution, because there won't be a corner solution, and it is equal to 0. And then we also look at the derivative with respect to root 2, and we get p2 minus lambda beta x1 to the power of alpha x2 to the power of beta minus 1, and that also must be equal to 0. And then we have basically the same thing that we get when we use this approach for the utility maximization problem. So we have p1 over p2 is equal to alpha divided by beta times x2 over x1. And then we can solve all of this. And we get, I'm skipping a few steps here. We get here that x1, and I'm just noticing that with an h, that this is different from what we have in the utility maximization problem. We get here that this is alpha divided by beta p2 over p1, beta over alpha plus beta, u bar 1 over alpha plus beta. And you get this by solving this for x2 and then plugging into the constraint again. But notice that your constraint is now the conditional on the utility. So basically, you have here the u bar is equal to this x1 to the power of alpha, and then you have here this x2 solved, which is x1 beta over alpha p1 over p2, and this entire thing to the power of beta, right? And then you solve and rearrange, you get into this expression that I have here, and we can do the same thing for the 2 until we get here that this is beta over alpha p1 over p2 alpha over p power of alpha over alpha plus beta times u bar 1 over alpha plus beta. So I know this is a bit algebraically intense, but I have no doubt that you can figure this out. If not, feel free to ask in the next lecture or ask in class, but we will do a few more of these problems. But the key point here is, what does this mean and what do these demands for the good now look like? Because they are different to what we've seen before. What comes out of the utility maximization problem? What's different?
We are trying to maximize our utility with limited budget.
Yeah.
Is it a difference?
Yes. So here we're trying to minimize our expenditures subject to reaching a certain level of utility, right? So it's just a different approach. But that is absolutely correct. But what do you notice when you're just looking at these demands here? What do they depend on? What is weird about them? Because if you're seeing them for the first time, they might look a little bit weird. Well, what is weird is that they depend on this u bar now, right? So all of a sudden we have this utility function, this utility level in there, but it's a little bit like, and obviously mathematically this comes from the constraint that we are facing, but then how do we interpret it and how do we deal with this and what do we learn from this, and also what does this mean, like how does this relate found under the utility maximization problem, right? Because I've told you, well, in the end, these two problems are the same, but it's not obvious if you're just looking at this, how are they the same, and how can we actually connect them, and how do we do this? And so here is the question, or here is how this is done, or this is a proposition of how people think about this. And so we have, in the utility maximization problem, we have a certain given wealth level. And we find that in this utility maximization problem, the X star is optimal. And then the argument is that this X star is also optimal when the required utility level equals exactly U of X star. So basically, if our U bar is equal to our maximized utility, then we get the equivalence. But what was our maximized utility level? Nothing else than our indirect utility function. So basically, we have our indirect utility function as this U bar, and if we were to plug this in from the expenditure minimization, from the utility maximization problem, we get exactly the same solution. And we can do the reverse thing. So what we're getting here is for a given utility level, we're getting the amounts that are consumed. So now you can plug these two demands. You can plug them into this P1 x1 plus P2 x2. You can set that equal to the wealth that is needed. And then, if this is the wealth you also have in the utility maximization problem, then you get also again the same demand for the goods in the utility maximization problem. So, just to summarize, suppose you have a solution to the utility maximization problem. That delivers your utility. You plug this utility into the expenditure minimization problem. It gives you the exact same amount. You then have an expenditure minimization problem that gives you an optimal demand for the goods. That leads to a level of expenditure of wealth that you need to actually buy these goods. You plug this wealth, you use this wealth as a level of wealth needed for the utility maximization problem, and again you get the same outcome. This is the connection. Now, this solution to this expenditure minimization problem is also called the Hicksian demand, right? So what we get out of the utility maximization problem, that was the Gaussian demand or the Marshallian demand, or just the regular demand that we are usually talking about. For the expenditure minimization problem, we get the Hicksian demand. And I also write, and I do this interchangeably, X of H, because you still ask for a certain quantity, and so sometimes I want to emphasize that you're still buying a certain quantity X, only now it's determined by the H and not by the Marshallian demand. And so when I want to distinguish between the two for the Marshallian demand, I write Xn. So these are the two differences. And so now we have found the solution to the expenditure minimization problem. And then the question is, what does this Hicksian demand look like? And in what space does it live? And how do we construct it? So many questions. So, one way to think about this is, as always, to start with
right side, and
Exactly. So that's a perfect answer. So our indifference curve, right, gives us all the bundles that are indifferent between that yield the same utility. So basically, we fix the utility. So this is important when we want to look at the Hicksian demand, because we're fixing utility here. So we basically want to illustrate this Hicksian demand, and here we have to for some fixed utility. So that's why I'm writing again the U bar. But I'm fixing the utility here, and I'm just looking at price changes again. And so the indifference curve gives me all of the points for which the utility is the same. And so that's why this is important to construct the Hicksian. And so now we want to understand how these price changes differ. So we have here one price. What is the slope of this straight line here that I added just now in terms of the price ratio?
X2 is much cheaper than this one.
No, the only thing you can see here is right that you're buying a lot more x2 over x1, but that does not give you the slope of this straight line. What is the slope of that straight line? If I know that this is what I'm buying, so a lot of x1 over x2, and I'm doing this optimally.
That is the optimal point.
Yeah.
It's close to X2.
No, this is my optimal point. So basically I have this for the price ratio. So this is my optimal point for that price ratio. So how optimal consumption will given the price ratio? But what do I know what the price ratio is? Because we know that at the indifference curve, where the indifference curve is tangent, we have that this price ratio must be minus P1 over P2. This simply comes out of the slope of the budget curve, right? So if we just want to calculate with the budget curve, so we always have M, or in our case W, is equal to P1 x1 plus P2 x2. So if we're solving this entire thing for x2 in order to calculate this budget curve, then what we get is we have M divided by P2 minus P1 over P2 x1, and so therefore we know that the slope of our budget is minus P1 over x2, and we know that at the optimum, the indifference curve and the budget line are tangent, and so this is the slope of the prices, right? So that's what we know. Now, given these prices that we just have, we then so these are pretty high prices. So as you correctly pointed out, this is our first, let's just keep it simple one, so we just fix P2 is equal to 1, and then we have here our first price, and this first price is pretty expensive, and what this means is that we have very little of x1, so here I'm somewhere at this point here. So the difference here, how much you're buying in terms of x1, that should also be reflected at this point. Now I can lower the price, but I'm still That's fine. And so we connect this, and that gives us our Higgschian demand, right? So this is what this looks like, and it looks a priori exactly the same as our Marchand demand, as a standard demand that we're knowing. I'm keeping the utility fixed. I look at what happens with the price, and it is this decreasing function. But now you know how you can derive this from any difference curve. Because the key thing is you need to keep the utility fixed. Other questions on that? Does it make sense? Makes sense. Excellent. Okay. So now we have constructed this Higgschian demand graph. So the Higgschian demand also has some nice properties. It is homogeneous of degree 0 in prices. Now we talk about homogeneity a bunch. What does this mean? If price is doubled, what happens to the demand?
So, divide 2.
No?
So divide the 2.
No, it stays exactly the same. Price is doubled, nothing changes in terms of the demand. They ask for the exact same thing. They're just going to be spending double the amount. But in order to reach the same utility level, right, because they still need to reach the same utility level, the relative prices have not changed. And so everything has just become more expensive. And so we don't have a wealth constraint, right, in a sense. And so they just need more money to buy to reach that utility level, but that's it. That's fine. Then there is no excess utility. I kind of assume this, but you can also show this more in a more sophisticated manner. But the iteration is really that you otherwise you want to minimize the problem, and in order to minimize your expenditure, you want to keep the utility as low as possible, because the higher utility means that you need to spend a little bit more. And finally, if the preferences are strictly convex, or such that the utility is strictly quasi-concave, then there is a unique solution to the expenditure minimization problem. And so that is nice, because then we have indeed a function. So we need this strict quasi-concavity of the utility function. So what is nice about the Higgschian demand function is that it fulfills the compensated law of demand. And the compensated law of demand means that prices and demand move in opposite direction. So if the price for a good goes up, then you buy less of the good. And if the price of the good goes down, you pay more of the good. What is important here, and this touches a little bit on this already in this homogeneity of degree 0, is that you're compensated here by the price changes, right? So because the Higgschian demand keeps the utility fixed, you can always reach this utility level. So this means if your prices, if all the goods that you want to buy become more expensive, then yeah, you just spend more, but you can spend more. You are in this sense compensated with an increase in wealth to be able to reach the same utility level. You might not want to do this, right? Because you might want to substitute away. So if just one good gets more expensive and the relative prices are changing, then you're going to choose different consumption models. But overall, you are compensated so that you can still afford the exact same consumption model, because that gives you the exact same utility. And this is why it's the compensated law of demand. And let me just emphasize one more thing. So the compensated law of demand, in terms of compensated law of demand a bunch of times. Again, I think this is one of the key insights, which is not trivial, and which sometimes also does not hold, but which is one of the tenets of economics, and one of the key insights overall of economics. So the fact that the demand curve is downward sloping demand, so now I'm just going now I told you already all of that. That's fine. So now we can turn to the expenditure function. So the same way that we talked about the value of the problem, the indirect utility function for the utility maximization problem, we can also look at the expenditure function. And the expenditure function just is how much you need to spend at the optimum, if you do everything right, in order to achieve the utility level that is specified. So you just plug in your optimal things here. And so this expenditure function now is homogeneous of degree 1. I feel like you're my homogeneous person now. What does it mean that it's homogeneous of degree 1? Or do you want to support him? No. Yeah.
It doesn't make any sense if we make the prices higher because demand and Angebot.
You can also say it in German if you feel more comfortable.
Yeah,
I will translate.
I did remember it. Demand and other supply will rise.
We don't have no supply or rise. We're in a partial equilibrium model. These things are like where prices come from and what happens with these things and where the wealth comes from. That is a general equilibrium question. We will get to this eventually, but for now, there's no supply, no demand. I think there's demand, but there's no supply. The supply is just given. That's why it's partial. But just the basics here. So we have an expenditure function which I'm arguing is homogeneous of degree 1. So that means that if I'm doubling prices, expenditure also doubles. Why does this make sense?
Because we need to keep our utility on the maximum.
Exactly. We need to keep our utility the same, right? If I'm doubling the prices, we have just seen that. Sorry. Here, let me go back to this. If we're doubling our prices, because this is what this means, then our Hicksian demand does not change at all. It is unchanged. We are still buying the same amount. And the reason we're doing this is exactly as your colleague said. This is because we still need to reach that utility level. Now, in order to be able to reach the utility level, and because we're keeping the stuff that we're buying the same, we're not changing, even though the prices are doubled, it means that we need to spend twice as much. We also have that the expenditure is strictly increasing in U. Why is that the case, or why is that reasonable?
Because we need more, sometimes we need more.
Exactly. And that is a really great answer. So we need so if we want to reach a higher utility level, we need to buy more stuff. Buying more stuff is more expensive, and so our expenditure should be increasing if we have a higher utility. It is non-decreasing in PL for any L. Why is that? That's the same logic as we have before. Same bit of remember. If my prices go up and I'm buying something of that good, then I need to spend more. So this is the increasing part. The non-decreasing part is meaning it can also stay constant. So non-decreasing just means it can either be increasing or it can stay constant. And the constant part comes about from, it might be the case that I'm not buying any of that good, that where we have the price increase, again, the yacht example. I am not buying a yacht, so therefore a price increase of yachts does not affect me, and then therefore the expenditure does not change. And we have that the expenditure argument with the price. Why the expenditure function is increasing the prices. So here we have P1. I'm assuming here price is the first good, that this is what we're looking at, and here we have our expenditure function on the vertical axis. So now, what happens as P1 increases with the demand for good X1, the Hitchin demand for X1?
Homogeneity is one, also saying it's one.
No. So if the price goes up, then what we do?
Okay, less demand.
Less demand. Right, perfect. So what you're doing is you have that H1 goes down, so the demand, the Hitchin demand for H1 goes down, but at the same time the demand for H2 goes up. And then we have the same argument that I already made before. If my price 1 goes to infinity, then my H1 gradually goes to 0. And so what this means is that eventually the expenditure just becomes a function of H2, and any further increase in P1 becomes irrelevant. And so initially, I'm still consuming something of good one, and so my prices are going my expenditures are going up, but less and less so, because I'm moving further and further away and getting closer and closer to 0 in terms of the H1. That's the intuition, what it looks like. Even that, I'm not super happy with, because I think it's still difficult to see. And so therefore, for this, I'm actually showing you the proof. So this is the proof of why, indeed, we have this concavity in prices, because, first of all, I think it's a nice introduction to proof. It's not super difficult, but it also, it's one of those things that you really cannot see without looking at the math. So, suppose we have two price vectors, and again, think of these price vectors to keep your imagination simple, as having two prices. So we have P1 prime and P2 prime, and P1 double prime and P2 double prime. And then we have, we're looking at concavity, and concavity is about mixture of things, and so we're mixing these two price vectors, and we're getting a price vector P bar. And so for concavity, what we need to show is this inequality here. So basically we need to show that the expenditure of this mixed price is higher than the mixture of the expenditure. Right? And so why does this mean that this is concave? Well, because this is definitely a concave function. We've seen this a bunch of times. And so here we have P1 prime, we have here P2 prime, no, it's not P2 prime, P1 double prime. Here we have somewhere in the middle alpha P1 prime plus 1 minus alpha P1 double prime, that is equal to our P bar 1. And so this lies above here. So this is our expenditure of P bar, and this is the mixture of the expenditure at this point here. This is our alpha E of P1 bar plus 1 minus alpha E P1 double prime. And so, because this is a concave function, this indeed always holds. Just graphically what we are after. And so,
Sorry, could you return to the slide for a moment?
sure, sorry.
Just for copy.
Yeah.
Thank you.